Every product claims to ship an AI agent. But look closely. Most of these systems aren't agents at all. They are fixed pipelines. The paper we are analyzing today categorizes these systems as agentic. In an agentic system, the cleverness doesn't live inside the neural network. It lives in the external scaffolding, the prompt chains, prescribed stages, and workflows engineered by the developer. You can add more API tools, loop in memory modules, or orchestrate complex subtasks, but that doesn't grant the model agency. It just yields a more elaborate agentic workflow. True agency, with the paper terms agentive, must emerge endogenously. The capabilities and the regulation of how to process information have to arise from within the model itself. Compare the execution paths. On the left, an agentic pipeline forces data through a fixed sequence of developer-defined stages. On the right, an agentive model dynamically updates its internal state, actively choosing its own routing. During inference, an agentive system regulates its own deliberation mode. It can react immediately to an emergency, or it can pause, simulating the consequences of an action before committing to a final path. Because of this internal architecture, it improves endogenously over time. Agentic systems, by contrast, only improve when an engineer manually rewrites the pipeline or schedules a new training run. If a developer explicitly dictates the workflow stages and hard-codes the logic paths, the system possesses no true agency, no matter how powerful the underlying language model is. To move past philosophical debate and into engineering reality, we need a rigorous operational test to determine if a model is actually agentive. The paper introduces a formal mathematical criterion for an agent model. Action must be generated strictly conditional on 3 specific variables. The first variable, S, is the current state. This is standard across all policy models. The critical variables are G for goal and I for identity. For a model to be agentive, these must exist as first-order, inspectable parameters within the conditioning set. Most systems currently deploy their goals and capabilities by baking them directly into the network weights or locking them as frozen, hard-coded system prompts. If the goal and the self-model are fixed by design, the model cannot update them dynamically. It fails the test, remaining merely agentic. True agency requires an internal architecture capable of inspecting, decomposing, and rewriting its own goal and identity variables during execution, entirely without retraining. Current frameworks often try to achieve complex reasoning by forcing a planning stage into every single loop of their execution workflow. This approach is essentially pure model predictive control, or MPC. Before taking a step, the model calculates a full simulated rollout of possible futures. There is a mathematical ceiling to this approach. Theorem 3 details the strict relationship between desired precision and required planning horizon. As you demand higher precision, the horizon scales logarithmically. The compute cost climbs at an unsustainable rate. Forcing a model to run a full simulated rollout just to execute a routine, trivial action burns processing power for zero gain. Conversely, when the model faces a highly novel problem, the fixed horizon set by a hard-coded pipeline is rarely deep enough to actually find the solution. Hard-coding a fixed deliberation stage creates a brittle system. An architecture can only scale if it possesses a mechanism to bypass planning entirely when it isn't mathematically necessary. The paper proposes the GIC architecture, Goal Identity Configurator, to solve this compute problem by splitting decision-making into 3 internal subsystems. System I is the reactive actor.
It handles routine execution and immediate emergency corrections, firing instantly without deliberation. System 2 is the simulative planner. It engages when the model faces high-stakes, novel situations, requiring deep counterfactual evaluation and rollout prediction. The core of the agentive model is System 3, the configurator. This acts as a learned meta-controller governing the other 2 systems. The configurator outputs a single regulation decision. It determines exactly when to deliberate, when to react, and when to learn. This is not a set of if-then rules written by a developer. The configurator is a dynamically trained parameter within the model itself. Internalizing this exact decision, the choice of how hard to think, is the mechanism that separates a true agentive model from an orchestrated workflow. When the configurator does decide to plan, System 2 requires a simulator. It has to accurately predict the consequences of its proposed actions. This introduces the load-bearing architectural principle of the GIC framework. The agent model must be functionally distinct from the world model. The distinct world model exists solely to answer what will happen, trained entirely on next state prediction. Conflating action selection and state prediction into a single model exposes the architecture to a catastrophic failure, the reward gradient. If the agent's reward objective reaches the world model's parameters, predictions become corrupted. By fencing off the model, that gradient strikes a structural wall. Without that barrier, you induce wishful simulation. The model begins hallucinating futures based on what it wants to happen to maximize reward, rather than predicting physical reality. The planning phase becomes useless. This brings us to Theorem 2. Simulative reasoning is mathematically viable only if the queried world model is already reasonably accurate. You cannot execute genuine simulative planning in a monolithic architecture. You must structurally fence off your oracle to guarantee the integrity of its predictions. The industry currently relies on fixed benchmark task success, but a high score on a static test often just rewards over-engineered scaffolding rather than true intelligence. The paper proposes an alternative framework to audit endogenous capability called PEG, Performance, Efficiency, and Growth. Performance evaluates generalizable reasoning across untrained tasks, moving past narrow domain competence. Efficiency directly tests the configurator. It measures whether the system actually spends more compute on harder problems while reacting instantly to simple ones. Growth charts the learning curve, measuring the model's ability to self-direct exploration and practice in simulation over time. If a system displays high task success but flatlines on efficiency and growth, it is not an agent. It is a highly optimized, developer-driven tool. We have to state the honest limits of this research. The GIC architecture is a conceptual framework, and concrete instantiations currently exist only as partial prototypes. Because of Theorem 2's strict requirement for world model accuracy, building a generalized open-world predictor without relying on reward gradients remains the primary unsolved bottleneck for the entire industry. But the diagnostic distinction holds. We have to separate competence hard-coded into a pipeline from capabilities internalized within the model itself. True agency demands first-order goal and identity variables that the model can actively inspect and dynamically update. Engineers need to stop mistaking bolted-on scaffolding for machine agency. Using this formal architectural standard, we can stop building elaborate pipelines and start building models that actually decide for themselves.